For the sake of the record, let me just say this again. So the question, so there is a question, and the question is the following. Last time we proved group theoretic angle, and let's recall the statement. Can you help me? Can you recount the statement? V finite dimensional vector space over K any field. So G is a sub of GLV, let's say, or you want to say, okay, G acts linearly on V. So G is just any abstract group. Okay.
Such that every element of G acts unipotently.
Yeah. Such that assume each element of G acts unipotently on V. Okay. Then there exists zero such that, which is a common fixed vector for all the elements of G. So such that GV is equal to V for all G in G. Right. So this was the statement, and so the first step was we may assume that, or right, and question is, now we are asking why may we assume? That's the question, right? In other words, so we have to show that if I know this statement for an algebraically closed field, then I know it for any field. Okay, so the answer is as follows. So think of V as a solution to a system of linear equations over the base field K. And this system is the following. You write G minus 1. So you think of this. So this is the that is the system you think of. Okay. Now if you, to make it more explicit, what we have is G is equal to, so say V has dimension n. So each G is represented so fix a, okay, so even before I do this, let's fix a K basis of K equals base field. So K is not algebraically closed now, not necessarily algebraically closed. Fix a K basis of V. Okay. So with respect to this basis, each G is represented as a fix it, let's say V1 Vn, okay, each as an n cross n matrix. Okay, let's call the, we also denoted G by abusive notation. Right now, so you may write, so to find V, so is equal to, so let's write x1, so any element of V is a linear combination of, uniquely a linear combination of these basis elements. So is the same thing as, to find V is the same thing as finding a solution of the system. So I write G minus identity n cross n. So now this is an n cross n matrix over K. Okay, so right now that's a system of linear equations. I mean infinitely many perhaps, but definitely a system. And the statement is, if you have a system of linear equations that is of the form A x1 x2 xn equal to 0, B x1 x2 xn equal to 0, etc. Okay, so each one of these is one this is a set of n equations, but as G varies you will get some, right? So it's clear how it is a system of equations, right? Okay, now so the statement is, if I have a system of equations and over K, that is if you have a matrix A and x1 x2 xn such that A x1 x2 xn is equal to, need not be homogeneous, but in this case homogeneous means what? This is 0. If this is 0, such a system is called homogeneous. If not, it's a non-homogeneous. Even if it is not homogeneous, if this, as long as the coefficients all live in the base field, and if you can solve it in over some extension field, then you can solve it below. Okay. Now you might ask why that is true. That's probably what you were asking. Okay. So let's see if okay, how see, this will be true because of the rank condition, if you wish. When does suppose I think of Ax equal to 0, when does this have a solution? When does it have a non-zero solution? When so when you row reduce echelon this, then I mean you can think in those terms. Anyway, I think that's an elementary exercise. If I'll let you think about that. If you insist, we can return to it next time, by all means. If there is any doubt or if you want me to do it, I will do it again, return to this and do this on Friday morning again. Okay, but don't hesitate. If you have a problem, by all means, let's revisit it. Okay. Is this all right now? Okay. Okay. So now coming to, can I borrow a book, please? Okay. Thanks. உங்களுக்கு ஞாபகம் இருந்தால் அந்த இதே சொல்லிடலாமா, இன்னொருத்தனை மாற்ற சொல்லிடலாமா? ஒன்று தான் இருக்குங்க, இல்லை சார் நிறைய சரியில்லை, ஒரு 2-3 இருந்தால் வசதியாக இருக்கும். மறந்து போகிறது எனக்கு. நீங்கள் okay. So there is more in chapter 2, this recovering a group from its representations. It's called, it goes by under the name of Tanaka. It's the name of a mathematician, and there is a whole genre of theorems that are called Tanakian theorems, or it is all of them of the nature of recovering a group by the knowledge of its representations. Okay, for now I will skip that. Okay, that is not an essential part of the text. Okay, so it can be skipped without any effect on the main storyline, so to speak. So for the moment we will skip that. At some point I might return to that. Okay, if not in class, then I might just give a colloquium talk or something on Tanaka, maybe because other people may be interested in it, and then you will be invited to attend that. Okay, be that as it may, for now we skip that and go on. So we are going to chapter 3 now. Okay. So this is, so if you, the subject of this chapter is tori. Okay, this is a plural for torus. We will define that in the course of that will be part of the lecture. Okay, so the title of chapter 3 is commutative algebraic groups. So, okay, it doesn't say linear, but you should say linear, I guess. So when something is commutative, then you can the first thing is you can prove some the structure simplifies in a certain sense, and the first thing is we see that tori are in particular commutative. They fall under the category of commutative linear algebraic groups. So once we understand the structure in this sense, we will be able to apply that to this. Okay. Okay. So and also this is a good thing, right? I mean, so we want to study linear algebraic groups. It's natural to study if the group is abelian, if the underlying group is abelian. What further can I say? Right? It's a very natural question. Okay, and okay, so here are, so these statements, now the book is a little terse. Okay, so for every line you might have to think a lot. Okay, so I will try to expand on every line here. I'll follow the book literally. Do not, just because it's a few pages, do not think that, oh, this is easy. So every line needs attention. Okay, so I want you to follow the logic very closely. Okay, so it's not you should look at it with with full skepticism. If something is not clear, don't assume. Make sure that you understand. It's a logical sequence that is important. Okay, so and as you will see in some parts of the proofs, in some of the proofs, they are very again like the proof of that when we saw that. What was that? Where he had that there exists in the Jordan decomposition. The proof was very short, but very very involved, tricky, and you make a certain construction which is not the first thing you might think of if you proceed if you were to proceed by yourself. Okay, similar things will happen here. So the point is you pay very close attention to every line. Okay, and if something is not clear, stop and ask. Okay, so also it is easy to make mistakes. Okay, so this Jordan decomposition is quite simple, of course, but there are pitfalls which many beginners are prone to fall into. So be aware of that. Okay. So theorem 3.1.1. Okay. G is a commutative linear algebraic group. Then 1 GS. So what do we mean by that now? The set of semi-simple elements of G, which is all those elements of G. Every element of G we know there is a Jordan decomposition. So every element of G can be written as GS times GU with certain properties. GS and GU are uniquely determined. You call an element semi-simple if it is equal to its. So GS is called the semi-simple part of G. GU is called the unipotent part of G. You call an element semi-simple if GU is equal to 1. In other words, so it is semi-simple. So this is the set of semi-simple elements, and GU are closed subgroups 2. And if I take GS cross GU to G, so this is multiplication, is an isomorphism of algebraic groups. So you can, if you have a commutative group, you can separate out the semi-simple parts, you can separate out the unipotent parts, and they will form closed subgroups. Okay, and the multiplication is an isomorphism of algebraic groups. Okay, that's the statement. Now, what is obvious here and what is it says GS and GU are closed subgroups, right? There are two parts here. They are closed subsets as varieties. They are Zariski closed in our G. So there is a topological statement and there is a group theoretic statement. Okay, so let's see which ones are. How about GU? Why is that closed? okay, claim. Okay, so we are beginning to prove certain. Okay, so these are, yeah, like I said, you. So here is the proof, and I will make several statements. Okay, watch out closely. So GU is in general closed, I want to claim, meaning without the assumption on commutativity. Okay, why is that? So the proof is here is as follows. You choose, when I write that I mean, of course it's not written, choose an embedding of G in GLN as a closed subgroup. Now, therefore, what is GU? This will be G intersect GLNU. Correct? This is, okay, let's see. GU is surely contained in G. GU, any element of GU, its image will be unipotent by preservation of Jordan decomposition under a homomorphism of algebraic group. So this is obvious. Conversely, if something belongs to G and to GLNU, because, so its image here is unipotent, but so if you have G here, say let's call this rho here. I mean, I'm by abuse of notation I'm not writing rho, but so rho G will be equal to rho GS times rho G U. Right? Now, if it belongs to, so what, which we are proving this way, right? Now, and also by the preservation of Jordan decomposition, I can write this is equal to, so this is equal to rho G of S, this is equal to rho G of U. Correct? To say that something belongs to GLNU means what? This is 0. I mean, this is identity. Okay? This is, right? If this is identity, but rho is an, therefore, this is equal to this, and that is identity, but rho is a injection, therefore, GS must be identity, and therefore, it must be unipotent. Okay, that's the formal proof, but anyway, there it is. Okay, so you can write this. Okay. Now, how can you, that's a closed set. What does it mean for a matrix to be unipotent? It means that minus 1 power n is equal to 0. Okay? I mean, absolutely, you can write any power, but in particular you can write n. Okay? So this is equal to G such that G minus 1 to the n equals 0. Now that's a system of equations, the solution to which is a Zariski closed set by definition. Right? Think of G as a matrix. So G minus 1 will be another matrix where you will have x1 1 minus 1 on the first entry, x2 2 minus 1 at the second 2 entry, but the others are just xij, and so the non-diagonal entries are just xij, and you are raising into the nth power, so you will get some equations. I mean, that will be some, each entry of that will be an nth degree polynomial in the entries of, in the xij, and you are setting each one of them equal to 0. That's that's like a n square equations, n square polynomial equations. Okay, whatever it is, it's some what we are not so much worried about the exact form of those equations at the moment, but the point is that they are they are polynomial equations. Okay, so it is a closed set. Okay, so this is closed. Now, GU, now see the whole thing is happening inside GLN, right? G is closed in GLN, GLN U is closed in GLN, therefore their intersection is closed in GLN, so the GU is closed in GLN, therefore it's closed in G. Correct? Or I mean, you can just say GLNU is closed in GLN, that intersect in G is closed in G. Okay, so this is the fact that this is closed is a general, holds in general. Okay, okay. How about GS? What do you think? Okay, now let's take an example of an algebraic group. What is an example of an algebraic group? Let's take the most obvious example. GLM. Let's say GL1. Okay, GL1. It's also called GM. I'll write that notation. GL1. What are the semi-simple elements? What are the unipotent elements? So GL1 sits inside so that's the which elements are nilpotent. I must get G minus 1 to the n equals 0, where G is now a scalar, meaning just one element of a field. So what is the solution to this equation? 1. So the only element which is unipotent is 1, which is a closed in that. Anything, how about, what about the other ones? They are semi-simple. Huh? Every element of GL1 is semi-simple, including 1. 1 happens to be both unipotent and semi-simple, indeed. That's correct. Okay? So, because GL1 is itself if I am giving you a matrix, to check something is semi-simple or unipotent, you just have to check whether that matrix is diagonal, semi-simple or unipotent. Okay, is that clear? See our definition. So see, while we have come a little distance, you should not forget the concrete part of it. Okay, so if I am giving you a matrix, to check whether it is semi-simple or unipotent is something that we know well before this course started. Okay, so indeed GL1, every element is it's in 1 cross 1 matrix, everything is semi-simple. It is diagonalizable. Well, it's diagonal. Okay, therefore everything is semi-simple. Only one is unipotent. Okay, so what is the semi-simple? So GS is in fact, okay, you might say it is closed in this case. Okay. Good. Okay. So GS turned out, GU turned out to be closed and equal to single point, proper closed. GS turned out to be the whole of the group. So that's also closed. Very good. How about, okay, so some other example we should try. How about GL2? What does it mean for a matrix to be semi-simple? So I'm asking this purely as you can think in terms of calculus. There are 4 x, y, z, w, 4 entries, and I want some condition in terms of the entries to say the matrix is semisimple or the matrix is unipotent. The matrix is unipotent is, of course, I write that 4 2 by 2 minus this 2 by 2, this is identity 2 by 2, I take the difference, raise is square equal to 0, that is what I write. Okay. Okay, so here is a, okay, I will say this in words, you just, it's a good exercise for you to write it out and make sure you understand this, and it's not just for GL2, for any GLM. Okay. So one way to think is it must have it must be diagonalizable. Okay. So to say it is diagonalizable means what? That it satisfies okay, so to make it slightly simpler, let us think about when it is regular semisimple, what is called regular semisimple. So an element is called regular semisimple if all its eigenvalues are distinct. Okay. So here is a condition for regular semisimple, and later on we will use this. You can actually write down a condition for when exactly it is semisimple, and we will use this later on in chapter 4. Okay, but the idea is the following. It's quite simple, it's all linear algebra, you've all studied this, but except maybe not in this, in the sense of putting all matrices together and thinking of it as a collection of matrices and a condition on matrices for it to be semisimple. Right? Okay, so here it is. So for it to be regular semisimple, it means that the characteristic polynomial must have distinct roots. Right? So so you write the characteristic polynomial. So if you are in dimension 2, you have t square minus trace of x or t plus determinant of t equal to 0, determinant of x equal to 0. Right? To say that this has distinct root means what? Distinct roots means what? It's just that usual b square minus 4ac is non-zero, right? Yeah, positive only if you are over real numbers, but we are over an algebraically closed field. So what do I, b square is trace square x square minus 4 ac. Right? Now that's an open condition. So what we get is, so let's write, if I write x, y, z, w, sorry, I'm writing x here and x here. Let me make this small x. Right? So let's write it out. So what is that? Plus 2xw and minus 4xw. Plus right? So as long as this equation is not, meaning that's a big set, right? It's a Zariski open set, because when you put it equal to 0, you get a closed set, right? And open sets, so, and this is it's an open set in this affine space. Even thinking in terms of not GLN, but even thinking in the bigger affine space, right? This is an irreducible space, irreducible as a topological, with the Zariski topology on it, it is an irreducible space, and any open set therefore is dense. So this is in particular, so you are leaving out only a, some kind of a very thin, right? It's a hypersurface, what's called a hypersurface. That is the locus of one equation. Okay, so it is it's far from being closed. Okay, it is in fact dense, right? So right, so this is very special, because we are assuming commutative, we are proving that this is in fact a closed there. Okay, let's see. So this part is all right. Why? Because G1, G2, so if I have, okay, so it comes because if two semisimple elements commute, their product is semisimple. Why? It just comes from the fact that if you take two diagonalizable matrices which commute, their product is diagonalizable. If you have two matrices which are unipotent, and if they commute, their product is unipotent. Well, how do you prove that? Very good. So let's see. So is this clear that if you have two semisimple elements which commute, then their product is semisimple? Because so this is diagonalizable, this is diagonalizable, and if they commute, you can simultaneously diagonalize. Okay, let's think about the proof of that. Okay, why can you simultaneously diagonalize? So the eigenspaces of one of them is stable by the other. So, correct? So if I think, because they commute, if I take, so let's take a fixed eigenspace of one of them, for the other it is stable, and therefore you can diagonalize that for that eigenspace, right? And then those, right? So you should review this, that if you take two semisimple elements which commute, for that matter any family of semisimple elements which commute, you can simultaneously diagonalizable elements which commute, you can simultaneously diagonalize them, right? So that shows, because you can put G inside some GLN, and then it becomes just matrices. Once I put G inside some GLN, all the theorems I have proved about Jordan decomposition just say that to find some element is semisimple or not, I just look at its image and see if that element is diagonalizable or not. Okay, so if I have two elements, their images are semisimple and they commute, then their product is also semisimple. Okay, now for unipotent, how do you do this? Suppose U is unipotent and V is unipotent, two matrices, U is unipotent, V is unipotent. How do you show UV is unipotent? Right, one way to do that would be, as Abhishek was suggesting, I have to show that 1 minus UV is nilpotent, right? So let's write this as 1 minus U plus U minus UV. And so you can write this as 1 minus U times U plus U times 1 minus V. Okay, I know that 1 minus U to the M is 0, say 1 minus V to the N equal to 0, and UV is equal to VU. So they commute, that's my assumption. Then if I raise this to the, what should I raise it to? This plus this minus 1. That's the least. I mean, of course you can raise it to anything higher. If I raise it, then because this commute, I can use the binomial theorem to expand. So this power, so doing this here, so 1 minus UV to the M plus N minus 1 if I take, claim is this is equal to 0 by binomial theorem, binomial expansion. Because if I expand this, then by the A plus B to the this, so either here there will be a power which is bigger than M, or here there will be a power which is bigger than N. Okay, so that's equal to, so that shows that a product is unipotent. So this is this, of course this uses commutativity. Don't forget that. This is only true if we are using commutativity here, because we are saying two semisimple elements, if I multiply them, and if they commute, their product is semisimple. Two unipotent elements, if I multiply them and if they commute, then the product is unipotent. I am using, so okay, so what remains is only that GS is closed. Okay, so for that, so okay. You can write GS, so choose or choose let me put V here. Okay, you choose an embedding. Okay, now I want to, I can find all the elements of GS are diagonalizable as endomorphisms of V. So and they commute. So I can choose in fact all elements of G, choose a basis for V consisting of common eigenvectors for elements of GS. Now claim so identify GLV with GLN with respect to that basis. Right? Each element of GS is diagonalizable, which means each element has a basis vector consisting of eigenvectors. Now they commute, therefore I have chosen a common one. Okay. Now the claim is, okay, what do elements of GS look like now in this basis? They look like diagonal. Now the claim is, I claim G is equal to Dn, so this is diagonal. Okay, why? This is by construction, right? Because I have chosen my basis such that each element of GS is represented by a diagonal. Now the converse is true in any case, because once I have this, once I have its injects, if the image is semi-simple, then it must have been semi-simple to begin with. So by preservation of GD, I mean for general reasons. G embeds. So the point is this is the key. Right? Once you have G sitting inside some GLN, then if an element is as an element of GLN, it is represented by a diagonal matrix. That means it better belong to GS. The problem is this, not this. This is true in general, but we have arranged so that this holds. Okay, and now Dn is closed in. Okay, now observe, Dn is closed in why? Because it is defined by the saying that all the other coordinates are 0. Okay, so Dn is closed in Gn, so this is closed in G. GS is closed in G. So we have proved 1. Okay, now let's prove 2. Okay, so tell me if it's obvious or not. Is there something to be proved here, or is it obvious? GS and GU are closed subgroups, therefore they are in their own right linear algebraic groups, So this is a linear algebraic group, this is a linear algebraic group, and this is a multiplication, right? So what is obvious, what is not obvious? What is there to be proved? Isomorphism of groups is obvious, you're saying. Okay, fine. Okay, so Gautam is saying isomorphism of groups is obvious. Okay, and I tend to agree. Okay, so what is there to prove? But that's just multiplication, no? The problem is you could have a map of varieties which is a bijection as sets, but the inverse need not be morphism. So the only question really is, so this is an isomorphism of groups is more or less obvious. That it's a morphism of varieties is obvious also because you are restricting the multiplication. Okay, that's also obvious. The only non-obvious part is to show that the reverse map is a morphism. Okay, so okay, so so the proof of 2. So as you can see, this is this is typical of this chapter of the arguments. They seem innocuous and simple, but you have to pay close attention to understand what is what is clear, what is not clear, what is not even true maybe. Okay, so proof of 2. I claim let's see, G2 okay, so okay, so choose this. I want to make it so that the okay, here is the idea. I want to say I want to get the reverse map, right? That means I will go from G. I want to the map is also clear. I just take G to its semi-simple part, G to its unipotent part. The map is also clear. So, but I have to show it's a morphism. The problem is a morphism. Okay. Now, how do I manage this? So, what I want to do is, I want to say that my choice of basis is such that, so I put it inside GLN, I think of these as matrices. Further, I want to arrange so that the semi-simple part is precisely what you see in the diagonal. See, it's not true in general that if I give you a upper triangular matrix, then what you see on the diagonal is the semi-simple part. That's not true, because well, if for example, if the diagonal entries are distinct, then it is semisimple as a whole. You understand what I'm saying? Suppose I give you an upper triangular matrix with entries distinct on the diagonal, distinct non-zero entries on the diagonal, then it's an invertible matrix with distinct eigenvalues, therefore it is semisimple itself. So its semisimple part is equal to itself, not the projection to the diagonal. Okay? So, but since all our, see, now again I am using the fact that G is commutative, so I can choose such that, so how do you say this? You have to okay, so choose a basis of V such that each so let's see how. All right. Now let's see this this is, I have to write this, it's obvious what I'm, okay, let me okay. So yeah, this is the same thing as okay, now claim is so that is really no different from the previous thing, right? So let me see. So e.g. Common eigenvectors, choose okay, so I don't, okay, this, okay, choose a basis of common eigenvectors vectors for all elements of GS. Right? So, in such a basis, or with respect to such a basis, GS, the matrix of GS is just the diagonal part of the matrix of G. And so, this is the crucial part. So, thus, the map is given by projection to the diagonal, which is a morphism. Let's see. Okay, this should be obvious, but let's see. So, I am using commutativity here, that the group is commutative. Okay. So, help me please. This should be fairly So, the thing to do is the following. So consider GS, right? So okay, why don't I leave this as a good exercise? Okay, this is just a linear algebra exercise. So, but remember the group is, I'm assuming that the group is commutative. Yeah.
Firstly, to write it on this basis itself, when choosing a basis for common eigenvectors also you are assuming commutativity.
Yes, I'm assuming commutative. Yes. Yes, I'm using commutativity, yes.
And then, so how are you concluding the, okay,
Therefore, the projection to the diagonal is a morphism.
so that means, G to
So
GS,
G to GS is a morphism. Okay, to finally finish the, so thus G to GS is a morphism. And G to GU is given by G going to G GS inverse. That's a morphism. Okay, and then if both projections are a morphism, then it's morphism to the product. Right. So this is the part. So some linear. So if you choose your basis carefully, then the semi-simple part is nothing but the projection to the diagonal. Okay. So let us do. Okay, that's just 2 paragraphs of the book. Okay. Okay. If moreover, so here further. Corollary 3.1.2, if G is connected, so are if further. That is because they are images of a connected, they are images under a connected because they are homomorphic images of G, because GS and GU are homomorphic images of G. Okay. Okay, then we come to the next proposition. So it's a statement about groups of very small dimension, namely dimension 1. Okay. It says if G is connected, the reason you put connected is because if not, then the theorem isn't true. For example, finite group. Remember, every finite group is can be thought of as an algebraic group, because you can put it inside some Sn by Cayley's theorem, and then Sn can be embedded. Just think of n cross n matrices, and any finite subset is a variety, is closed. If you haven't proved this exercise, you should do so. Okay, so any finite subset of an is a closed Zariski closed. So you have to you can write down a set of equations which will satisfy this whose loci of solutions is precisely this set of points. Okay. So connected linear algebraic group of dimension 1. Then the conclusion is G is commutative. Then 2, either GS equals G or GU equals G. 3, if G is unipotent, and that is if G equals GU and characteristic of the underlying field is bigger than equals P, is positive, then every element of G other than 1 has order P. Okay, again this is quite a tricky proof, so you should pay close attention. Okay, so the proof goes as follows. Consider G to G. This is a map of varieties or more. It's not a group homomorphism. So fix G in G, and I can take X2, XG X inverse. Right? So what is that map? It is the under the, so it's a, you can think it of as the orbit of G under the conjugation map. Right? It's the orbit of G under the conjugation map. What all can you say about the image? What is surely in the image? G, right? Because 1 is there. Or G, if I put x equal to G or x equal to 1, I get G, right? So G is in the image. So let's call this a name, phi or something. Okay? Image phi. And right? Okay. What do I know about, what can I say about image of phi? Connected, but so in the, it's more than connected. See, connected, you say just because you, for traditional reasons, it is irreducible. Okay, so it's irreducible. Because it's the image under a continuous map of an irreducible set. Okay, therefore, if I take im phi bar, this is irreducible. Therefore, this is irreducible. Closures of irreducibles are irreducible. That's very easy to see. Okay, so this is irreducible, and it's contained here. Right? Now what can you say? This is an irreducible closed set. This is an irreducible closed set, and the dimension is 1. Dimension is 1 means any chain of irreducible closed sets. So you start with 1, you go next, and then you can't go any further. It has length 1, right? Which means this must be equal to this, or this must be equal to this. Okay, because dimension G is equal to 1, you have im phi bar equal to G, or im phi bar equal to G. Okay. Now the claim is, yes. Okay, assume, so suppose this. So we are done if this is so, then we are done, right? Because yes, and G was arbitrary. Yeah, so everything commutes, right? So so enough to show that, so enough to assume im phi bar equals G and arrive at a contradiction. Right? Okay. Now, one more thing. What do I know about im phi? Im phi bar equals G, right? Therefore, im phi contains an open subset of its closure. So im phi contains an open subset, non-empty open subset of G. So I'm assuming this. All right. Okay, now let's see what do non-empty open subsets of G look like. So its complement is closed.
So we proved that an orbit is open in its closure, and image phi is just the orbit of G. So image phi is anyway open in its closure.
Image phi is open in its closure. Okay. Okay. So it's a yeah, I don't think that gives us much. Okay, you're right, but okay, so claim is, this tells us, so what we've seen in, okay, claim is, shows again because of dimension 1. Okay, why? Let's see. Let's see this carefully. So, so if you have, okay, because, so let O be non-empty. So I'll do this. You're right that IMPhi itself is open in its closure. Therefore, IMPhi is open in G, but I'm not going to use it here.
So can we say this? So when every orbit, so since G was arbitrary, every orbit is therefore open in G.
Yes.
So, but we know that closed orbits exist. So there's one orbit which is both closed and open, but G was connected. So there's
No. Wait a second. No. Wait a second. Okay.
closure we assume is G.
No. For example, no, I don't think that will give you, because closed orbits exist, because see that G acting on this G by conjugation, right? So closed orbits exist because the identity is itself closed. Okay, so that I don't think that gives you any leverage in this situation. Okay, but by all means think, I encourage you to think along. Okay, so let O be a non-empty open set of G. So what G minus O is a closed set, right? G minus O is a Noetherian closed set. So G minus O is a closed set, and therefore it is a union of irreducible closed sets. Okay, but what are irreducible closed sets of G? Either they are points or it's all of G. Okay, so G minus O is a closed set. It is therefore it is a union of irreducible closed sets, finite union of. But any irreducible closed set of G is either non-empty, is non-empty closed set, or all of G. So we are done that G minus O is finite. Okay. Now, so thus, okay. Now, so thus, the claim is proved. I've written G minus. Okay. Now, okay, so far I think although we've used the see, so far although we have used the irreducibility of G or connectedness of G, it's not really crucially used yet. Okay, it is now that it is going to be used really crucially. Okay. So what do we, okay, so what do we know? So the point is, as x varies, this covers all elements of G except finitely many, right? So, and all of these have the same characteristic polynomial. So the point now is, so choose okay. Now the characteristic, so by the above, G going to characteristic polynomial of G consider, okay, has finitely many values. Because most of them have, I mean, so everything is in the image of right, correct, and the rest remains is finite. Okay. Now the coefficients of the characteristic polynomial are continuous functions. So they are, you know, what do? You take you write out a matrix, you write out its, you know, character, you know, it's a polynomial in the entries of G, right? Okay. So it is taking finitely many values, but now therefore you get, but G is connected. So the coefficients are all functions which take finitely many values. Since G is connected, that value must be the same. Let's see. Since G is connected, what we conclude is, we are not done yet. The characteristic polynomial is constant. Okay. Now
all the polynomials are the same.
Algebraic polynomials, there's one.
I mean, there's only one.
There's only one
static
The
polynomial.
remain is one.
yes, I meant
Okay.
it's not that it is the constant polynomial, but okay, as a function it is constant. That's what I meant. Okay. So and equal to now that's because one has this characteristic polynomial. So the identity matrix occurs as the image. Therefore, that has this characteristic polynomial. Therefore, everything has this characteristic polynomial. So conclusion is, implies G. Okay. So thus G is unipotent. Okay, hence solvable. Okay, now look at GG. Now that's an irreducible closed. So it's the irreducible closed subgroup. It is solvable, so it cannot be equal to G, and therefore it must be the identity which moves G is commutative.
Why is not that? What did you say? The last thing you said is not that type.
So let's look at it again. GG cannot be equal to G because I have shown that it is solvable, which means it cannot be in particular perfect because it has to go down the series, right? Okay. So thus, okay, now GG is what? Is an irreducible subgroup. Is a connected subgroup. Right, and it is not equal to G. Because G is solvable. Okay, so but it is irreducible. So so what are irreducible subsets of G? It has to be a singleton. So which means G is commutative. Well, let's see. I mean, we got it. I mean, well, that doesn't make sense. I mean, it's strange, isn't it? I mean, we arrived at a contradiction. So it's I don't know if maybe you can try to clean up the proof even more, because it seems a little strange that we arrived at a contradiction. Okay, because then G is commutative, then this is
The contradiction we got was the fact that G is commutative.
yes, the contradiction we got is the fact that G is commutative. Yes. So we are done with one. Yeah, because so this possibility is not there. So this is true, though, which means this is G, which means every element commutes with G. So we did this. Okay. Now, okay. So the other parts are these are irreducible closed subgroups, and their product is equal to G. So either this is 0, one of them is 1, the other is okay. Okay. This is also fairly easy. This is, but anyway, now I'm well over time, so we'll pick this thread up. Okay. So next time we will do 3.2, and so as to the logistics, maybe definitely 2 more turns we should be well into chapter 3 and about finished, because I'm going to skip 3.3 as well. 3.3 except for a statement of 3.4.9, I'm going to skip the rest of we are going to do only 3.1 and 3.2 and the statement of 3.4.9. Okay, and then move on to chapter 4. So we'll be done with chapter 3 by Wednesday. Definitely next week we'll be done. Okay, and when is the schedule for the exam? So we are done. Thank you. Sure.